All right, so we got ionic. I think that's all I want to say about ionic. Oh, how come they don't conduct to solids? How come that right there won't conduct? But they will conduct if you put it in water or melt it. The ions are stable, they're static, they're stuck. Electricity needs motion. So there's two things electricity can flow through. Mobile electrons, like metals, which we're going to talk about next, or mobile ions. So when these ions get broken apart, for whatever reason, you're melting it, you're dissolving it in water, now your ions are moving, so your electricity can flow. Okay, next, so there's ionic. This is metallic. Notice the difference. They're both positive, negative, but here, these are valence electrons. So metallic bonding, you have a sea of electrons with your positive cation. So that's the difference. The crystal structure, the lattice structure, is basically the same as far as there's different types, the body center, face center. So the way these rows are like packed together, again, like the ornaments in a box or whatever helps you understand, the packing, the crystal structures are the same. There's no difference really. It's just this is one metal. So these are all, let's say, copper ions or iron or zinc or whatever metal we're talking about. And these are the valence electrons that are freely moving around. So what are you writing in metallic or underneath metallic? You're writing it uses Coulombic force, just like ionic, but the difference, these are electrons, not anions. All right? These are electrons, not anions. So you would think, well, maybe this could be packed more efficiently because you don't have those anions in the way. Well, remember, the positives will repel each other, so they can't get too close, so that affects it as well. But the reason metals are so strong is because of the Coulombic force. You have positive cations and negative valence electrons, so these are also very strong. All right, so again, there's your ionic, and then there's your metallic, and you can substitute in whatever you want. But these, again, would be copper +2, or sodium +1, or gold +3, whatever it is. And then these would be the valence electrons. All right. Metals conduct electricity because these valence electrons are free to move. You can bend metal because if you hit this hard enough, the force will cause the cations to slide on the sea of electrons. The analogy I use with this is boats. You have boats anchored, let's say, or tied to a dock, and there's a long enough rope or whatever you're tying it to. If you push the boat, even a big boat, you push it hard enough, you can get it to move on the water. That's what bending is all about, malleability, ductile. So you can always bend it back, right? You get a dent in your car door, you can usually go on the other side and bang it back out. It's not too bad. Same concept here. All right, and this is why you can do that, because they slide on the sea of electrons. So you could say sea of electrons on an AP test. That's fine. I prefer mobile valence electrons. That's like the better way to say it. But, all right. There's a lot, not a lot, but we need to learn about alloys in AP Chem. In Regents, I briefly mention it. Things like bronze, for example. That's zinc and copper, or steel is a alloy. But in AP, which we're going to talk about this later, there's two different types. There's substitutional alloys, that's like bronze, and then steel, which is interstitial. So the difference is steel, the red ones would be iron, and the green ones would be carbon. You take little atoms and stick them in between the spaces. Again, that's the packing. So if we filled this whole floor up with basketballs, there'd be a diamond shape in between the basketballs. Right? If you took 4 basketballs and put them together, it'd be a big space in the middle, it looks like a diamond. Well, if you took something like a softball and put it in that space, it's making it more efficient, more tightly packed. That's what steel is. Substitutional is when you take an atom out and put another one in that's basically the same size. So if you have a floor full of basketballs and you take some basketballs out and replace it with, a soccer ball is about the same size probably. So the soccer ball isn't a basketball, so that's why that's the blue one. So it replaces it, it's called substitutional, and it changes the properties of the metals. So anyways, alloys are usually stronger and harder than pure metals, and it's because of what you're doing to it. We'll talk more about that down the road. let's see. This is a molecular solid. It's the best image I can give you of a molecular solid. Molecular solid uses weak forces. These dotted lines are weak forces. So in your notes, if you need to write molecular solids, molecular substances, use covalent bonding, but there's weak forces between the molecules. So what I showed you guys the other day, or maybe it was Chi-Chi, I don't know, but if you take, did I do this yesterday, Chi-Chi?
Yep.
Okay. So if I drew this on the board, it's a great example of what molecular is all about. So methane is very weak. Well, sorry, that one's a little, let me fix that. So methane's very weak. It uses dispersion forces to hold itself together. So the confusing part is, well, what's the difference between covalent and molecular? And that's because Regents kind of screws you over there. But the bonds here and here and here, those 4 bonds, are covalent. And yes, those are pretty strong. But when you do anything to methane, phase changes, physical changes, what you're doing is you're breaking or reforming dispersion. So these forces are extremely weak, which is why methane's a gas. Has very low melting point, low boiling point. So molecular substances are extremely weak because they use forces to hold themselves together, not bonds. Network covalent doesn't have them. It's just all bonds. That's the big difference. I hope that makes sense. So that's what molecular solids are all about, or molecular substances. They use mostly dispersion. All right, I'm going to erase this. I need some space here. They use mostly dispersion forces. I know I'm talking a lot today, but yell out the other ones. What are the other weak forces? Dipole, dipole. So dipole forces. What else? What's the strongest of the weakest? Hydrogen bonds. H bonds. So you got dispersion, dipole. Those are the biggest ones. Hydrogen bonds are dipoles. They're just much stronger. And remember, that's NO or F with hydrogen. H with NO or F. There's another one called induced dipole. And I definitely don't have time to get into all these. I was hoping I could get into these, but we can do that Monday. So you got dispersion, dipole, H bonds, induced dipoles. And then there is one more force that kind of is a combination of things. I might as well just bring it up here now, is ion molecule. Or molecule ion, either one. I forget how I worded it. The AP kind of words it a little differently. In Regents, I call it ion or molecule ion. Basically, what it means is you have an anion or cation attracted to a molecule like this. So that's kind of a separate thing we'll talk about. But these are the 4 that hold molecular together. All right. And I should have ranked them here. This is the strongest. All right. And then dispersion is the weakest. I think you guys already know that. Dipole is similar here, so it's fairly strong, stronger than dispersion. And induced dipole is a little stronger than dispersion, but weaker than dipole. I know it's a little confusing. If you just know who's strongest and weakest, that's good enough. Let's see, what else did I want to mention? Oh, the big thing with molecular and the AP, like here's this giant book that I have to make sure you have to know everything in here. Which is no problem. They talk a little bit about substrate and enzymes. You guys remember that from biology? The lock and key method.
Yep.
So not just the shape. So here's your substrates, and here's your enzyme. So this one has a triangle. This one has like a little bump to it. They're only going to fit, lock and key again if the shape fits. But the shape is dictated by these forces. So there's a lot of hydrogen bonding, dispersion, a lot of these forces going on in your body when you have enzymes and substrates doing their thing. The same thing goes for lipids. You guys remember the hydrophobic, hydrophilic tails, the polar head, and does this ring a bell a little bit? Again, this is hydrogen bonding, and so this is the basis for why these lipid bilayers do what they do. right? So water is going to be attracted, and the polar heads are attracted to the water, but not on the interior. And again, that's because of the forces of attraction. Last thing I just want to mention here, this is a protein, and this is another picture of a protein. Proteins have very bizarre shapes. They twist and bend on each other, and a lot of it has to do with this, how their forces interact with water and other polar and non-polar substances. So I just wanted to throw that out there. It's not something I'm going to like make a big deal about, but a lot of the biological processes in your body only do what they do because of the forces and the types of bonds that they have, especially polar and non-polar. It's a big deal. So I just kind of ripped through as much as I could there. I'm out of time. Monday I'm going to have to talk about forces. I'll text the homework because I don't have time right now. So do me a favor. On Monday, come in ready with a rough, like, maybe 1 through 10 step of your procedure. What are you going to do in the lab? I know I'm putting a lot on you there, but you're big boys and girls, you can do it. All right, come in with just like a bullet list. I'm going to do this, this, and this to figure out the bonding of the unknown substances.
What about our partners?
Yeah, what if our partners aren't the same?
Like, what do you want?
I'll pick the partners and text them.
You already picked.